we're going to figure this out. Aaron, are you okay? Okay. You may not need to calculate on it, I know. Alright, so let's get rocking with checking last night's homework. Now, for you guys, I think part A isn't what I have up here on the board. This is probably the work you did for part B. Part A should look something like that.
Yeah.
Right, where it just said using your calculator to determine the exact value of the integral from 0 to 8R of TDT. And you get 1,133.071 gallons. Is everybody okay with that? All answers have to be accurate to 3 decimal places. Non-negotiable there. All right, in terms of what this means,
Okay, we go.
more than 3 is fine, but at least 3 is the minimum expectation. So the integral from 0 to 8, this is going to say from t equals 0 to t equals 8 minutes, a total of 1,133 blah, blah, blah gallons that leaked out of the pool. Are you okay? Okay. Now, part B, I think, is this question where now I ask you to do like a left endpoint approximation. Is that what part B was?
Yes.
Oh, okay. So it should be 1 times R of 0, 1 times R of 1, 1 times R of 2. Of course, you don't have to have the 1s, but your final answer needs to be 1,262.0714 gallons. If you're using F instead of R, that's a bad thing, because there is no F here, it's just R. All right, I think the rest of this handout matches, but maybe not, we'll see. Okay, part C, I think I asked you, using the right endpoint method and 5 rectangles, approximate the value from 0 to 10. And I got 925.401. It's awfully quiet. 402. Or 925.402. We're okay? Oh, maybe it's quiet because it's up too darn high. And then because RT is a decreasing function, the estimate is going to have to be an underestimate if you're using that endpoint method. All right, part D, now it's the left endpoint method and 4 rectangles, and you should get 2,128.764 gallons. And the other one, 665.350 gallons. These numbers are all matching up, okay? So based on your answer to part D, what would be a reasonable estimate? Well, if the left endpoint method, I'm all sticky apparently, if the left endpoint method is telling me an overestimate of 2128, and the right endpoint method is giving me an underestimate of 665, then a really smart choice for what you think the actual area is somewhere in between these two, right? Any number in between those two would be fine, but probably the best choice would be to find the middle, right? To find the average, like that would be your best choice so that you minimize the error. If you went with the middle, you go with 1,397, and then your error is no more than 731 gallons. Good. All right. Then part F, those are the numbers you should have, 1,200 and some change. And the other one, 1,198 and some change. Part G, how much is actually in the pool after 20 minutes? Well, if the water was leaking out of the pool for 20 minutes, and I started with 2,000 gallons, you're just going to subtract those two values to get 659 gallons. How'd last night's homework go? For the most part, everybody doing okay? Alright, good. So, Carmen, if you wouldn't mind doing your thing, just go around and pick them up. Thank you. Alright, we got 4, get 7, we got 10, still no Celeste. Alright, a couple of quick announcements. Oh yeah, be careful tearing these things out.
I'm getting better.
Okay, so I'm curious, would you all prefer that for the problem set packet, 1 staple?
Yes.
1 staple for the problem set packet? The problem set packet is usually the tinier one, so I think 1 staple for that, it'll make tearing stuff out easier. What? It'll rip easier if it's one staple.
Meaning it's going to become loose.
Did you say grip?
We're talking about the other one.
Oh no, the student packet will continue to have 2 staples because that sucker's pretty big. It's the problem set packet because that's what you guys are tearing out. All right, let's talk about tonight's homework, which is a quiz. Yay! Are you okay?
Yeah.
Is it the word quiz that causes you to have like strong reactions? So what if I said like major assessment? What would that do to you?
The same reaction.
Same reaction. Okay. You're like talking about study for
I
now?
just know it's hard for me.
All right. No, this is meant to be a short quiz. Okay. Just for some perspective. No, you don't have to.
Oh, it is?
Okay. The short quiz. Last year I gave the BC students 20 minutes and they had too much time. So this might actually only be a 15-minute quiz that you're going to do tonight at home. Yes. It is brief. It is all calculator active. You're going to be just fine. Okay.
Are you going to be here after school?
I am going to be, where am I going to be? Today I'm going to be at Southwest, then I'm going to be at Southeast, then I'm going to be at North Side. So no. Tomorrow I'm going to be here, then I'm going to be at North Side, then I'm going to be at North Forest. Okay, I just wanted to go over my whole itinerary. Sorry, North Central, still not getting over to you all. Tomorrow, because I need to be at Northside and North Forest, I'm not going to be able to be here in the afternoon for tutorials, support, quality time. Sorry, I got no choice. All right, so here's the goal for today. You guys can put away the little quizzy poop. The goal for today, you don't need the student packet. We're going off book. We're gonna go off, but we're going into day 2 of Riemann Sums. Stephen, are we already filming? Yep. Okay. What I want to do is take some time to make sure everybody is 100% okay with the stuff we did yesterday with Riemann's method. Okay. There is a part of this that I really care deeply about. I will let you know when we get there, because those of you that are like, oh my God, my head was going to explode. And yesterday, when everyone else was clapping, when we got to 39, I was just clapping because it meant it was over. Wherever it is that you were on that spectrum, I'm going to give you an opportunity to either continue going deeper with me or opt out and get some practice. And wherever you are, that's fine, no judging. Giselle, you okay there? All right, so let's go through the big picture. So recap of Riemann's process. Integral from a to b of f of x dx, you guys know, just means you got some curve. We're going to go from some starting point to some ending point. My goal is to find the area. What does Riemann tell us to do? What does Riemann tell you to do?
Make a rectangle.
We're gonna make rectangles. I think he tells you to do something before that, though. We've got this interval from a to b that we're trying to find the area bounded by the function and the x-axis on that interval. But Riemann says the first thing that we're going to have to do is begins with a P. Partition. Partition is just a fancy word for chop it up. How are you going to chop it up? Now Lewis is like, let's set the bar low, 4. Okay? It could have been 4 equal subintervals. It could have been n equal subintervals. In fact, Riemann never put on the stipulation that they had to even be equal widths. It doesn't have to be. For the sake of our not losing our mind, let's say that we're going to go with n rectangles of equal width. Well, then my first question is, how wide is each rectangle going to be? N rectangles, equal width. How do we determine the width of each rectangle? What are we going to do?
Well, first,
B minus A.
yeah.
Right? The interval that you're interested in is from A to B. So first of all, I take that length, which is B minus A. And then what? And then I'm going to divide that up into n equal subintervals. If you've got an equal subinterval, then this is how you're going to find the width of each subinterval. I then partition my interval, and just so it can be a little bit bigger, I'm just going to draw that not to scale. Let's go A to B. And the first subinterval starts at A, and it ends at A plus whatever that width happens to be. That's what I'm using as my delta x. The next interval goes from A plus delta x all the way over to this next part. How far is that? Right, wouldn't that be A plus delta x again, A plus 2 delta x? I'm going to alternate these, like one above, one below, so I get more space. A plus 3 delta x, A plus 4 delta x, and I'm just going to keep chopping up my interval as long as I need to reach that last point. All right, so let's do a method. I'm really a big fan of the right endpoint method. The College Board seems to be a big fan of the right endpoint method. So let's get some hands on this. First rectangle, right endpoint method. What I'm interested in is the area. Somebody tell me how we're going to find that first area. Let's get some hands on this. Area for that first rectangle. How wide, how tall? Lewis, tell me how wide, how tall?
Wide is delta x.
Right, the width is delta x. How tall?
Would be f of a plus delta x.
F of whatever a plus delta x is. That's if I'm using the right endpoint method. Now if I'm using the left endpoint method, what's the different Palomar if I'm going to use the left endpoint method here?
Using the left, you're going to be under.
It looks like the way that I've drawn the graph it would be under, but in terms of the way I'd find the area of the rectangle, what would be different if it's the left endpoint method? It would be f of a, right? The width doesn't change. What changes is how I determine the height of the rectangle. Am I using the y value on the left or the y value on the right? Your other options? Midpoint method. We're going to stay away from that. Other method? Trapezoid method. For now, we're going to stick with right endpoint methods. That's the first one. Allie, tell me about that second rectangle. What's the area for the second one?
Change in x
Yep, delta x.
times f of a plus 2 times change in x.
F of a plus 2 delta x. Love it. And we get to the third one. Giselle, how do you find the area for that third one?
Delta x f of a plus 2 delta x.
F of a plus 3 delta x, right? And we're going to keep on going and going and going and going and going until we get to this last one. And this last one, with like that's the nth rectangle. Myra, what's the area for that last rectangle?
Delta
Delta x.
x times
F of n, not f of n. Remember, the way you determine the height
n delta.
would be f of, you started at a and you added on delta x. How many times? Right, f of a plus n times delta x. Now there's another way you could have represented a plus n times delta x. Lewis, what are you thinking back there?
B.
Isn't that f of b? Now, check out the mathematics here. If delta x is b minus a over n, multiply this by n, what you get is b minus a. Add that on to a, what do you get? Because we're looking at
that.
a plus n times this expression here. N times b minus a over n, the n's
Equals
cancel.
B.
A plus b minus a is f of b. Is that exactly where I want it to be? It's exactly where I want it to be. This is good. This is solid. But what gets really exciting was the piece that we layered on yesterday. A better way to write this, a faster way to write this. This is the thing that I care deeply about. Have a conversation with your neighbors. How are you going to write this more efficiently? Oh, I'm hearing it in all corners of the room. We get some sigma notation. Okay, and you're just like leaving them there? You know the street value of this stuff, Carmen?
Yeah, Carmen.
Like, at least like a quarter. Alright, let's get some hands on this. Clever things you can do to make your life better. Myra, what do you got for me?
Take out the delta x.
Okay, you could absolutely take out the delta x, and then you're going to have like f of a plus delta x, f of a plus 2 delta x, 3 delta x, blah, 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 blah. But there's something even better, something even more powerful. Aaron, what's more powerful?
Notation.
What if I try expressing all of this in sigma notation?
Can you still keep the delta x there?
There's a lot of things you can do with the delta x, and we'll talk about what you can do in a little bit.
Okay.
Sigma notation means sum. It always means sum. You need a counter and a starting value, and you need an ending value. Pick something for your counter, it doesn't matter. I'm gonna start with k. I like k for Keith. And we're gonna start at 1. Where do we stop counting? When would we stop the addition process?
B? We start with B?
The counter is how many times you're gonna use this expression. So this is like k equals 1 over here. This guy over here is gonna be for k equals 2. K equals 3. When do I stop? When k is n. And n is just the number of rectangles. Lewis?
Would K always be 1?
Great question. No.
No.
K just is going to be your counter. You can start anywhere. You could start at 0 if you wanted to. You could start at 1,000,000 if you wanted to. You could have negative values. There's no rule for what this bottom value is. The rule is you got to have one, and the counter changes by 1 every single time. How long?
Does that mean that's how we'd be able to differentiate from left from right?
Yes, if you were doing a left endpoint method, you might want to adjust your counter to start at 0. It would be a little more clever to do it that way. We're going to spend a whole unit playing around with this. All right, so let's do the sum. We're going from k equals 1 to k equals n. Now what I need is the summand, like this part in here. How do I represent all of these in one nice compact way? Well, they all have the form delta x times f of something. Now let's look at the f of something. A plus delta x when k equals 1. A plus 2 delta x when k is equal to 2. A plus 3 delta x when k is equal to 3. How am I going to write this in here?
A plus
A plus,
K delta.
we want to be careful. There's definitely something getting multiplied by the delta x. It's the k value. The k is the counter. K is the only thing in this problem that's changing. A is a constant. Once you tell me where to start, I've locked it in. My width is constant for the problem. The width is constant. The n also a constant. The only variable here, the only thing allowed to change is the k value. Everybody okay? All right, so what this tells me, this is the exact answer. This is an estimate. Why an estimate? I want to get some hands on this. Why is this not the exact answer? Why is this only an estimate? This is really going to reveal some deep stuff. Have a conversation with somebody near you. Why isn't that giving you the exact areas?
It's the sum of the rectangles.
That's an estimate, not the exact answer, because why, Andrew? Why is this only an estimate?
Because just like
Yeah, but you start
Okay,
from the
Carmen
left.
has shushed you.
You start from the left.
Aaron, shh. Carmen has shushed you.
Oh, sorry.
Okay, Andrew?
Because it's just like rewriting what you did in top, so it's like what you wrote in top is just going to be a estimate, so when you rewrite it, it's the same.
I am confident that you know this is an estimate. I'm not 100% sure that you know why this is an estimate. Aaron, help him out. Why is this an estimate?
Because with that notation is the sum of the endpoint method that you use, which is still an estimate.
It's the sum of the areas of all of these rectangles, and this actually isn't giving the exact area because sometimes I'm getting overestimate, sometimes I'm getting underestimate. So I'm going to call this guy here like A of n or A sub n. This is how I'm going to approximate the area. Riemann's thing. This was the thing for Riemann. How do we get to an exact answer? How do you go from estimate, that's all this guy is, that's all it can be. Lewis, how do we go from an estimate to the exact area?
You write as limit of x as n approaches infinity.
Right, to get to the exact value, what you do is you take an infinite number of rectangles instead, and you do a sum from 1 to n of delta x, f of a plus k times delta x. It's in that limit process that you actually get this definite integral. This is the thing that I care greatly about. I cannot emphasize how much I care about this setup part. The stuff that we did after this yesterday to like evaluate it and the properties of segment notation was the bonus stuff. Is everybody mostly okay getting here? So here's what I want you guys to do. Show me what you can do with this first model problem. Your goal is to take all the information that I've given to you and come up with this expression. Okay? We'll talk in a little bit.
So this the one with the right. Yes. K is just a concept. So from 2 to 4, we can say you take it 1 because 3 plus 1 just means 2. You're thinking if they like the start with the x value, but it's not. K is just K constant. It's like if I go from that's not K. That would be this and that would be the top number. But that's not K.
Okay, how we doing? So, if you're not 100% sure what to do there, you could go through this process again. Where did we start in this process? What was the first thing that we had to really do? You had to find the width of each rectangle. How wide would each rectangle be? Right, you're going to take the length of the interval, which is 2, and you're going to partition that into subintervals that are all equal in length. So it should be 2 over n. Then where? Everybody go from there. Okay, and if you need to do that, feel free to do that. But if you think you can jump straight to this last part, that's okay too.
Yeah, what you got? What you got?
I'm saying 4 over n. You just have to take out the n. I'm saying 4 over n.
All right, let's kind of pull this together. Yep. Okay, let's stand back. All right, if I could pull everybody back together, I just need you guys for a couple minutes, and then we're going to split the group and figure out challenge by choice. I'm just going to draw like a quick sketch. I don't need to know exactly what the graph of 2x squared minus x plus 3 looks like. I'm just doing that there as like a placeholder. I know I'm going from 2 to 4. The first thing I'd want to know is how wide is each rectangle? What's that width? Width is 4 minus 2 over n, so 2 over n. The width is really important. Then you're going to say, all right, well, if I'm going to go from 2 to 4, and I'm going to partition my interval, and the width of each rectangle is 2 over n, this first rectangle goes from 2, and then where does it end? Where's this end point? The width of each rectangle is 2 over n. What's the x-coordinate for this one? It's not 2 over n.
It's 2 plus 2.
You're starting at 2. Did you say 2 plus? I didn't hear the 2 plus, sorry.
Yeah.
2 plus 2 over n. I have a different starting point. The next one, 2 plus 4 over n, 2 plus 6 over n, and keep on going. So if I'm going to approximate this integral here, we're going to say it's the width of the first rectangle, is that 2 over n, and then f of 2 plus 2 over n. Your next rectangle, 2 over n, f of 2 plus 4 over n. Keep on going until you get to the last one, 2 over n times f of 2 plus 2 over n. Well, how many times?
Okay.
How many rectangles did you use to chop up this subinterval?
And
You used n. So when you get to the last one, first one, second one, third one, fourth one, that last one has to be rectangle n. So this would be 2 plus 2 over n times n, not k yet. Not k. This is just that generic expression. If you need to write that out first, feel free. For those of you that feel like, you know what, I know I can go straight to big sigma here. Where do I start my counter? Let's see, if this is k equals 1 and this is k equals 2, that guy over there is k equals n, then my sum is going to go from k equals 1 to n. The width of each rectangle is 2 over n. And then this is f of 2 plus 2 over n times k. How many guys were able to set that up? Feeling pretty good? Okay, not the exact answer. Lewis, how do we get to the exact answer?
Limit as n approaches infinity.
Okay, limit as n approaches infinity. That's what this definite integral is equal to. Quite honestly, if you can set that up, that's about all you need to be able to do. That truly is about all you're going to have to do in an AB calculus class. Good news, also in a BC calculus class. This is about as far as you have to go. But there are some of you that are hungry for more.
I'm pretty full.
And I know where you are, and I'm going to get you.
Pretty full. Yeah.
We're going to go past this. Now, one thing that the College Board is going to do on a pretty regular basis to push you is they're going to ask you to actually don't leave it as f of all the stuff. Actually plug this stuff into f and like show me like what it would look like as a specific function. Let me write it out. Limit as n approaches infinity, k goes from 1 to n. 2 over n times f of all the stuff means 2 times 2 plus 2 over n k squared minus 2 plus 2 over n times k plus 3. Right? All they want you to do is evaluate your function at this expression over here.
Do that on the free response?
On the free response, they might ask you to do this. What's more likely to happen, Aaron, is on the multiple choice. I think a lot of you guys are going to be able to get to this setup like really quickly. You can like plug in the pieces. But you might be like, wait, I don't see this answer because they actually went one step further. I cannot imagine the College Board asking you to go any further than this. They're not going to ask you to go any further than that. I'm not going to ask you to go any further than this. Okay? All the friends are good? Alright, so this is where we get to challenge by choice. It is your choice. For those of you that just want to practice at this level, which is like, here's the definite integral, set up the region, I'm going to ask you to move to that side of the room. For those of you that want to stay, hold on, you don't even know what the other option is. Everyone's like, I'm out. For those of you that want to play around with properties of definite integrals and to actually like evaluate this sucker down to a final answer, stay over here. That's what I'm going to be doing for the next little bit of time. Now you can move. If you're over here, we're working through that definite integral. If you're going over there, you're going over to the back. Fine, It'll just be me, Mr. Link, Carmen, and the kids from North Central and East End. The kids at North Central and East End are like moving so they can't see the camera now, maybe. I don't know. All right, so Carmen's gonna stay. David, you're staying. Lewis, you just like pain. Okay, you guys are over there, and Ilay and Andrew, you guys are working on the back. Okay, so it's just the 4 of us. Just the 4 of us. We can make it if we try. No. All right, for the friends on this side of the room, what you are working on is the back. My solutions are over here. I'm going to leave them with Ilay. Or I'm just going to throw them on the floor. Okay, Ilay's got them. You guys can definitely help each other out. But if you could go in whisper mode, friends over here, we are going well past College Board expectations. Pretty good?
Yeah.
Okay. But before we go any further, are the 3 of you 100% okay getting here? Like, this makes sense?
Yeah.
How are you feeling about your abilities to like jump to this part? This feels good? Like going from the original integral to this expression.
Yeah.
Like maybe without even doing this part. Okay, right, like I'm doing this part over here so like we can see all the pieces, but what should be happening in your brain, you're like, no, like I figured out the pattern, I know how this works. It's this next part. It's this next part what's going to be a while. Alright, do you guys have this part written down? Alright, so the goal is to actually evaluate that definite integral. Back in the day when I was in Calc 1, this was a part of Calculus 1. But that's not the case anymore. I'm just going to take go. Alright. So we're at limit as n approaches infinity. And we had a sum. K goes from 1 to n, 2 over n.
Look back.
2 plus 2 over n k squared minus 2 plus 2 over n k plus.
I said the same. I said the same.
All right. Yes. Whisper. Or maybe move back a little bit more. Moving back would be better. Okay. So what I need first, legal algebra. Legal algebra, only legal algebra. What do you want to factor? Oh, but I don't think you're factoring. Wrong word. Right, you're like expanding this expression here. All right, so let's expand that. So if we're going to expand that, that means 2 plus 2 over nk times 2 plus 2 over nk. Do the box if you need to, but really what we're doing is we're saying 2 times 2, that's 4. 2 times 2 over nk should be 4 over n times k. 2 over n times k times this 2 over here is another 4 over n times k. And then the last one, 2 over nk times 2 over nk, that one's a little bit tricky. 2 over nk times 2 over nk is 4 over n squared times k squared. Now be careful, because all that you just did is just a little bit of side work to do this expansion. We still need to be careful and say, all right, so I need the limit as n approaches infinity, big sum here. K goes from 1 to n. 2 over n, big brackets. We've handled the square. I need to multiply everything by 2. So I'm going to like multiply everything over there by 2. So we're going to get, what is this, 8? 8 over n times k. Yep.
What do you be forgetting about that too?
That 2. Right, this work we just did was to expand the square. And now I'm multiplying by 2. And really, if I was being clever and had my A game here, I wouldn't write 8 over nk and 8 over n times k. I'd just write 16 over n times k. So plus 16 over n times k plus, what do we say, 8 over n squared k squared. That's the first part. Distribute that negative minus 2 over nk plus 3. All right, if there's any other cleaning up that we can do, we should do it. It would make your life better. Josh, what do you think?
The 8,
The 8, the negative 2, and the 3, I can combine all those together. Is that going to give me the 9? Anything else?
It's just 16 over nk.
16 over nk.
Minus 2 over n.
So that's going to give me, what is that, 14? 14 over n times k plus 8 over n squared k squared. That's just all the stuff in the brackets. We're not done. I still have the 2 over n in front. I'm still doing this sum. And I still need to take that limit. I need to see all the pieces. Okay. There's one more step of algebra that you might want to do. Like pretty good. I could like distribute that 2 over n through. And so if you do that, we've got limit n approaches infinity. We're going k equals 1 to n. What is that? 18 over n plus 28 over n squared k plus 16 over n cubed k squared. Friends back here, how are we doing? You guys comparing your work to mine?
Wait, where's your work?
Like I said, we'll play back the film if we need to, but ILA has it. Alright, friends up here, we're okay? So, now, the only thing standing between us and the final answer is a whole lot of sigma notation stuff that you didn't learn last year in pre-calculus. So, legal things that you can do is you can take the sigma, because this just means sum, you can distribute it over addition and subtraction. Just like you can do with the definite integral. That was one of the properties of the definite integral. You could break things up. So we're going to say that we've got now limit as n approaches infinity, a big sum, k goes from 1 to n, 18 over n, plus big sum, k goes from 1 to n, 28 over n squared k, plus big sum, k goes from 1 to n, 16 over n cubed k squared. Yeah. Not necessarily in the brackets. Is everybody okay with going from the 1 sum to the 3 sums? The reason that you would do this has to do with the fact that once you're here, when it comes to summing, any constants that you have, anything that doesn't change in the summing process, can get factored out in front. So in this first expression over here, what's a constant? The 18's a constant for sure. The n's a constant as well. Why? I think this is the thing that always catches people by surprise. Like, it looks like a variable, but think about what the n represents. K is your counter in this sigma notation. In the summing process, k is changing. K is 1, it's 2, it's 3. The n will change. Which means, you okay there, David? That I can factor the 18 over n out in front, and I'm summing from 1 to n. Well, what is it that I'm summing? 1. And I bet you know what that's equal to. Add 1, and then again, and again, and again, and again. When do you stop? When I've done it n times. Okay, plus, let's look at this next one. Where are the constants? For this next sigma.
Since n is
28 clearly the constant.
Yeah, and then just.
And the n squared is also the constant, because k is the counter, k is the thing that's changing. So 28, I want the 28 over n squared, sum over k, plus k goes from 1 to n, constants over here, I know you guys have figured this out, the 16 and the n cubed are constants, and what you're left with now is you're summing over k squared. It's this guy here
Say I.
that we're gonna take the limit as n approaches infinity. I'm gonna go check in with those guys. What I want you guys to do is check out your notes from yesterday. There were those fancy summing formulas that you had not been exposed to yet that you don't need to memorize. I'm not going to assess you on them. I just want to see if you can go from here to the next step. I'll be back. Because I'm sure. So how did I get these area values? Is that the question? So I was just like testing like we're not kids. Okay. Friends over here, how are we doing? Well, for the mortals in the room, they don't actually know how to find the antiderivative of sine of x and evaluate it from 0 to 3. And they also don't know how to do this.
Oh, I remember.
This one, I don't even think you know how to do that. I did not mean to offend you. Alright, back to the good looking people over here. So we've got the limit as n approaches infinity. 18 over n, I'm summing over 1. So this is 18 over n times, what's the formula? N. Okay. Plus the next one, we have 28 over n squared. The formula for summing over k. This just means 1 plus 2 plus 3 plus 4 plus 5. I stop at n. What's that equal to? N. N times n plus 1 over 2. That's just a formula that you would look up if you needed it. Over here, we've got 16 over n cubed, sum over k squared. 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. Again, there's a formula here. Don't need to have it memorized, just need to know that it exists. And the formula here? And n plus 1 times 2n plus 1 over 6.
X equals 3.
Things are looking good. I think you guys were like on the cusp of being finished. Now let's see. If we use your limit properties, right? Take the limit as n approaches infinity. What happens to 18 over n times n if I'm taking the limit as n approaches infinity? 18. Right here, you could even see the n's canceling out, and you're like, oh, 18 plus this guy over here.
And then the other end.
I can cancel out an n in both places, leaves an n in the denominator. Now, here's where I gotta be careful. This n doesn't cancel with that n. This is n plus 1, this is n over here. Sure, I can reduce the 28 and the 2, and I'm gonna get 14. The piece that we need to keep in mind is we're taking the limit as n approaches infinity. As n gets big, what happens to 14 times n plus 1 over n? You would have 14n plus 14, right? And the degree there is 1. You'd have n in the denominator, the degree there is 1. When there's a tie in the degrees and you're taking a limit as n approaches infinity, you look at the coefficients. So you would just be 14. Let's see if we can pull it off with the last one here.
It's like this.
You're just, if the degrees are the same, you look at the coefficients. What's the degree in the numerator here? Let's even skip the canceling part. The degree, n times n plus 1 times 2n plus 1 is an n cubed in the denominator. N cubed, good news, a tie. N cubed in the top, n cubed in the bottom. The only thing I need from you guys is, what's the actual coefficient in the top, and what's the coefficient in the bottom?
She's saying why didn't the 2 and the 9 add up
16.
like you?
over 6.
Put it square.
I don't agree with 16 over 6.
Square.
If we're looking at the coefficient, think about what happens. Where does the n cubed come from? It's the n times the n times the 2n. So you'd have 2n cubed times 16. So you've got like a 32n cubed plus some stuff in the numerator. You've got a 6n cubed in the denominator. When I take the limit as n approaches infinity, what we're going to get is 32 over 6. So what survives is 18 plus 14 plus 32 over 6. And I'm not even going to worry too much about your ability to simplify. And I'll tell you, the final answer, I think, is 112 over 3. Riemann, back in the 1860s, would have been able to go through this whole process, come up with the answer of 112 over 3, no calculator, no sketch pad, nothing. Just some incredible properties of segmentation. Now, so that I'm not lying to you guys, can you actually make sure this is the right answer? How can we figure out if this is actually the right answer? Okay, David's reaching for the calculator. What are you going to type into the calculator? I don't think you're going to type this into the calculator. Right, remember, all of this is an attempt to evaluate the integral from 2 to 4 of 2x squared minus x plus 3. Oh my gosh. I'm going to hope we're going to get 112 over 3. Lewis is so excited he can't even reach for his calculator. It's just watch. Let them do it. Just sit here and watch. You focus on David. I'll focus on Carmen.
I got 37.33.
37.3333.
Yeah.
112 divided by 3, 37.3333. Beautiful. Did you get 112 over 3? Wow, I really thought we were going to win the competition here. I didn't know I was backing a losing horse. Okay. Everybody okay? And for the folks watching at home, AB students, BC students are not going to be assessed on all of this stuff. This was just bonus innings, go as far as we can. Okay? Tonight's homework is just that short quiz. What I want you guys to do with the couple minutes that you have left, do this check for understanding, do this one completely on your own, and then see if you can do at least one more. For anybody that would like to have a bonus 100 on a homework assignment, you can just like bank this for the future. I will give you until Thursday to do the thing at the bottom that says Beast Point Opportunity. Okay, great. Well then finish it. Okay? But I want to make sure this is super clear. Like, you're like doing this. Right? So you're going to like show me the setup, and then you're actually going to like work through and get the final answer. You can have until Thursday. Alright, I'm going to check in with the friends over here. And oh my god, if you think you're going to cram it into this teeny tiny little space.
Yeah. But we don't know
Okay.
there. Because we get it, but like, yeah.
Now here's the thing though, I'm going to expect that you can go a little bit further. I'm not going to leave it as f of 3 over n k.
Well, he does this. I remember this one.
Exactly, right, which I hope for your brains is
Yeah, but why? Where did
right, oh, you're just plugging it into the original function. And what did you guys get for the check function?
I remember this is but we forgot the 4 plus negative.
Oh,
And that's
from
how
the.
you're
So these things,
right,
okay,
there's going to
okay.
be some simplification you can do after the formula.
Yeah, they're like stuck.
I didn't even know it's multiple choice until I read it.
It's just giving me so much. Now it makes so much sense.
So,
I didn't give it.
X cubed is okay, Adley and Andrew, how are we doing?
Good with the setup.
You need to show this actually. You call me.
Where the x squared? Should it be supposed to be s squared and then?
Well, no, you gotta
It's
go
not?
from, just like we did over here where I gave you like an integral, and then like you made it to the setup,
Yeah.
that's where I need to get you. You're starting like from the beginning.
Yeah, B.
Palamon, you're having a wardrobe malfunction back there.